This video should explain the differences between 16 bits and 24 bits analog to digital converters. In the beginning, I will explain a little of background. Let's suppose the analog voltage signal. We can get it from vibration sensor or, for example, from signal generator. We need to convert this signal to the digital form. How to do it? We need to read the samples. You can imagine that like voltmeter, which is moving through the signal. We will write the amplitudes to the table. This is the analog signal in digital form. Now we can apply the inverse procedure and draw the signal. The accuracy of a voltmeter is the key factor of the conversion quality. If the voltmeter can measure with precision 1 volt, it means we can get just volts. It means 1 volt, 2 volts, 3 volts, and so on. Now we repeat the measurement. If we draw the signal from that values, it doesn't look well. Now the voltmeter can measure also half volts. The signal looks better. If the voltmeter accuracy is 1/4 volt, the signal looks almost like the analog signal. The question is how often the voltmeter reads the values. The examples which we used had 20 samples in one period. Now we will use 5 times higher number. It means 100 samples. There is also context with aliasing problem. These matters we will explain in other video. The accuracy is made by the analog to digital converter chip. Chips can have various number of bits. How to understand these bit numbers? We need to know a little about numbers which we use. The decimal numbers we use in real life. The decimal system contains 10 digits from 0 to 9. But the electronic world doesn't use decimal system. It uses the binary system where just 2 digits exist. It is number 0 and number 1. The electronic devices understand that low voltage level means the number 0 and higher voltage level means number 1. Because we live in decimal world, it is not easy to read binary numbers for us. For example, this number is equal 41. How to get this number? It is easy. Each digit in number represents some power of number 2. Our example contains just 6 digits. These powers we can rewrite to decimal numbers. Now we are very close to understanding of the conversion. I write the binary number below. And now I multiply the rows. We get this. The last step is to do the summary of all numbers together. The sum is 41. Please try to make inverse process as homework. It means try to convert, for example, 35 number to binary format. Now you understand how the computer works with numbers. It uses binary numbers and it means also the converters from analog to digital give us binary numbers. Each AD converter has the voltage range in which it can work. For example, we use the converter with plus-minus 12 volts range. When the sensor sensitivity is 100 millivolts per G, then we can operate with plus minus 120 G's acceleration range. If the higher amplitude comes, it is converted to the maximum value. For example, the 150 G's is converted to 120 G's. Now we introduce the key factor of each converter. It is the resolution. The resolution is a number, and it defines something like stripes inside the measurement range. Actually, the resolution is the number of stripes. For example, when the resolution is 16, then the measurement range contains 16 stripes. Now I apologize to pure electronic guys. I know that the stripes are a little moved and the zero stripe is around the zero voltage level. These stripes explain how the converter works. For example, when the voltage level is plus 5 volts, then the converter returns number plus 4.5 volts. When the voltage level is minus 7 volts, then the converter returns number minus 6 volts. We know the width of stripes. That is why we can recalculate the stripe number back to the voltage, but not completely exactly. When we multiply the stripe number 3 by the width 1.5 volts, we get the 4.5 volts. But the measured voltage was 5 volts. If converter returns the half of width levels, then we get 5.25 voltage, but it also is not 5. This example showed to you that inside one stripe I am not able to distinguish the real measured value. We just know that it is inside this stripe. It means that all possible values inside one stripe is converted to the same stripe number. This example shows the pure sign converted to digital form by our converter with resolution 16. The digital signal doesn't look very good. It is the consequence of very wide stripes. When the resolution would be higher, then we get better digital signal. The resolution is defined in bits, not in decimal numbers. For example, our converter with 16 stripes is 4 bits type. The highest digital number in 4 bits is 1111. It means we get 16 stripes from 0 to 15. Every next bit will multiply the resolution by number 2. 5 bits gives 32. 6 bits gives 64. 7 bits gives 128. And 8 bits gives 256. The first widely used converters were 8-bit type. They work with plus 128 levels and minus 128 levels, together 256 levels. 12-bit converters work with plus 2000 levels and minus 2000 levels, together 4000 levels. 16-bit converters work with more than plus 32,000 levels and minus 32,000 levels, together more than 65,000 levels. You can see the long time interval between 16 and 24-bit converters. It is because 24-bit converters use totally different sigma-delta technology. 24-bit converters were a huge step forward. It works with more than 60 million levels. What are the consequences in practice? We talked about the voltage range plus minus 12 volts, which enables to measure 120 G's peak. The sensor sensitivity is 100 millivolts per G. If we use the sensor with 10 millivolts per G sensitivity, then we can measure 1200 G's peak. The plus-minus 12 volts range so looks as optimal. If we return back to the 8-bit converter, then we have range plus and minus 128 levels. Now I apologize again to pure electronic guys. I know that AD converters doesn't work with plus-minus 12 volts range. The typical ranges are below 5 volts. But it means to use just simple divider to get required range. What is the stripe width? It is 93 millivolts. It is almost 1 G. It is too much. It means that everything between 0 and 1 G drops to 1 stripe. Everything between 1 and 2 Gs drops to next stripe. It is clear that 8-bit for complete plus-minus 12 volts range is not the solution. Here you can see the stripe width for 16 bits converter. This value is much better than 8-bit value. But the question remains the same. Is it enough? The answer is it is not. Look at the next example. The upper signal has 24 bits resolution. The lower signal has 16 bits resolution. You can see the differences. The normal signals in practice can have only several millivolts and we need to measure them. It means we would work just with 10 or 20 lowest levels from 32 thousandths which are available. Imagine the scale 32 meters long. And you just use first 20 millimeters for measurement. It is bad news. You need better scale. Because around the year 2000, mostly 16 bits converters were available, so the analyzers had to use them. But they could not use them for full volts range. The low signal levels had to be amplified firstly and then converted to digital form. The low-level signal on the picture has to be amplified. If we used 16 bits resolution for full plus-minus 12 volts range, then the step is 0.3 millivolts. The signal maximum amplitude is 3 millivolts. It means we would use just 10 positive stripes and 10 negative stripes. The signal would be distorted. This signal uses the gain 500ths. Now the signal maximum is the quarter of full range plus-minus 12 volts. That is what we want. Now 10,000 steps will be used. Such gain enables good analysis. How is it done in practice? After we started the measurement, first the gain must be found. The auto-gaining procedure starts. The analyzer measures the peak signal value and set the proper gain. Now the measurement starts. It seems to be fine. Everything is okay. But no, it is not. The first, but not main problem, is the lost time. For low-speed machine, the auto-gain may take 10 seconds for 1 point. It means 1 minute for machine with 6 points and 1 hour for 60 machines. If you have to measure hundreds of machines, then it is significantly wasted time. But the main problem is different. If the auto-gaining uses the low signal level part without shocks, then the incorrect gain is set. When the shock then comes during the measurement, then the range is overloaded. The measurement in this case is either stopped or not, but then contains overloaded incorrect samples. All mentioned troubles don't exist if you use 24 bits converter. The level or stripe width is 1.4 microvolts. If we have the signal with 1.4 millivolts peak, then the converter doesn't need any gaining because 1000 levels are used for conversion. And this is the main goal. The 24 bits converter works always in full range. This is old adage analyzer with 16 bits converter. If the unexpected shock comes, it ruins the measurement. The next example is with adage VA5 analyzer. It contains 24 bits converter. We measure the machine and again unexpected shocks come. The measurement continues without any problem. You can use next test for any analyzer. Place the sensor to something soft and run the measurement. After the auto-gaining, take the sensor and knock to the table. No warning or error has not to appear. The measurement must continue without overloaded problem. Do you want to buy new analyzer? Pay attention how many bits uses the AD converter. If less than 24 bits, then it's not recommended to buy it. Thank you for watching.